So as most science courses should do, we need to kind of take a look at the scientific method. So sciences are not just knowledge. It's possible to have knowledge of something, to be able to observe something, but it doesn't necessarily, a set of observations haven't necessarily undergone the scientific method of reasoning. Scientific method of reasoning is just kind of, it's what makes sense sort of thing, and I'll show it to you here in a minute. But again, knowledge doesn't necessarily translate to a body of knowledge into a body of science, okay? And I think that science is misunderstood in many ways, and this is one of the ways it's misunderstood. So, for instance, you're probably familiar with, you've heard of hypothesis, if you've studied science at all and gone through the scientific method. To me, it's important to distinguish between hypothesis and theory. So a hypothesis is an early on stage, and like you see, what's happened is a curious person, such as yourself, has made observations. You've come up with a thought of maybe what's going on with regard to those observations. You've come up with a question that you wanted answered, and then you've come up with, based upon your curiosity and your observations, come up with a hypothesis. It's an educated guess. Hypothesis isn't just a wild guess, but it's based upon your observations and what you know. I mentioned that science is awesome because it just kind of keeps building on itself. And so you are building on what others in your area have to tell you, have to show you. So you come up with a hypothesis, okay? So based upon your hypothesis, your understanding of, or your thoughts about how things are working, you should be able to make a prediction. So then, based upon your prediction came from your hypothesis. If you're right, then you can, from your prediction, create an experiment to test your hypothesis. So scientists are all about pushing the envelope. Are we really right? Are we really right? Are they really right? Okay. So sometimes our tests, our experiments will say, hey, no, we weren't right, okay? Sometimes our predictions, what we thought should happen, doesn't happen. And then we need to, like this says, come back up and either modify our hypothesis or throw the whole educated guess out and start from scratch, okay? The other possibility is that, yes, you made a prediction, you tested your prediction with experiment or experiments, and it validated your original hypothesis. So you don't stop there. So this little loop right here, okay, after your hypothesis, you make a prediction, you test your prediction, or you test your hypothesis, you go back around. If it's right, you go ahead, based upon the same hypothesis, make a different prediction, or test it again. Okay, so this loop right here, we do several times. Several's a small number too. I kind of tease that scientists are kind of like a bunch of little kids in that they want to prove each other wrong. So once somebody publishes a hypothesis, scientists are already at it saying, is that right? Is that right? Maybe excited to prove it right, or maybe trying to prove it wrong. So if in this loop something doesn't, our experiment, our hypothesis fails basically, then we need to modify our hypothesis, okay? So if after that loop several times, the person who proposed the hypothesis and others in that area, if we continue to get validation of the original hypothesis, then it can be brought up to a theory. Your hypothesis is elevated to a theory. And I kind of liken it to if you play checkers, and if you struggle across to your board to your opponent's area, all the way over to his start, okay, you're playing checkers. Now, you could have gotten jumped, a lot of things could have happened, but you make it across. Then your opponent must king you. Okay, you get two checkers on top of each other. And that's what kind of a scientific theory is. It's, I made it across. I may be kinged, a scientific theory. Okay? So I think I have a slide on it, but basically when somebody says, that's just a theory, well, dang it. If it's a theory that has survived this process, then that is a theory that started out as a hypothesis with rigorous testing, and it was kinged a theory, so not just a theory. So if somebody says, I have a study of science, then in general, that those observations, like the science of astronomy is an offshoot of the science of physics. The things that happen with regard to the study of physics, the science of physics, happen because of natural causes, ultimately because of natural causes. Now, granted, physicists will, I think, be the first to admit, and so will chemists, that we're still understanding those natural causes. We know a lot, but we're still looking to understand, but it's explainable. In contrast to, there is some mystic power, some divine power that is pulling the strings. No, there's a set of laws, okay, that ultimately then the laws break out into these various aspects or theories of the way matter behaves and scientifically. So this is not to say that, and we can talk about this outside of class, this is not to say that miracles don't happen and just kind of breaking of rules don't happen, because I think they do, but that's not science. That's something else. That's usually our faith. So another hallmark of if it is a science or not is that it needs to be relatively straightforward, relatively simple. I know that our imaginations run wild sometimes, and we like to put little twists on things, like Ptolemy back in when he still thought that the Earth was at the center of the orbiting planets, the planets orbited the Earth, and the sun orbited the Earth. Okay, what Ptolemy did was to put kind of a complicated twist by making those planets orbit the Earth and kind of have little loop-de-loop or epicycles to explain that retrograde motion. Now, remember I said in my lectures recently, I said the KISS principle, keep it simple, stupid. That's what science needs to be. Okay, it can't be like your imagination run wild. Okay, and generally that's called Occam's razor. The simplest explanation that actually covers all the observations, the better. Another thing, and you saw this in the scientific method, is that the reality that you can test your hypothesis is important. Okay, if somebody throws something out there and says, this is my hypothesis, this is how it is, and you can't test it, well, that's not fair. Okay, that would not be, the person who's saying that's hypothesis, that can't be science. Science needs to be testable. You need to be able to sink your teeth into it. Okay. So this is my little bit about, it's just a theory. Well, if it's a scientific theory, then like I said a minute ago, then there has to be actually observations or multiple observations that theory explains. Okay, and you oftentimes, especially for instance, the Big Bang theory. I mean, we can look at the origins of our universe from all sorts of different angles, and it wasn't always that way over time. We've looked at kind of all the way around the Big Bang, the origins of the universe, and that body of evidence still supports the Big Bang. And so this was the thing about, remember, we go the loop a lot of times. The whole, from my hypothesis, I have predictions. I set up experiments or tests to test those predictions, and you go and hopefully you continue to validate the results of your experiments, validate your original hypothesis. So just to kind of sum up, this is a pretty good flowchart of the scientific method, and just to emphasize again that this is not a simple process. It's a makes sense process. But if a hypothesis survives this process and is elevated to a scientific theory, then it's no small feat.